All across the Earth, the history of life and of the planet itself is written in its rocks. Fossils, large and small, are embedded in rocks layered on top of each other. And by traversing these layers, now exposed at the surface, paleontologists can take a trip through time. Travelling back about 66 million years, rock layers all over the world preserve a remarkable transition from a world ruled by giants to one reeling from their sudden absence. Rock layers older than 66 million years belong to the Cretaceous period, the third and final age of dinosaurs. Improbably huge fossils are the remains of improbably gigantic creatures that roamed the land surface and ocean depths, grazing, hunting, living every conceivable lifestyle on this ancient Earth. But the rocks younger than 66 million years tell a very different story. Here, at the beginning of the Paleogene, the fossils are vastly diminished, both in number and in size. They tell of a world devoid of dinosaurs, stripped of its giants entirely. No four-legged animal weighing more than 25 kilos lives in this new world. They are mostly small, among which are our own ancestors. And it is a quiet, empty world in which just 25% of Cretaceous species remain. This is the Cretaceous-Paleogene boundary, a line frozen between worlds, an Armageddon marked in stone, unimaginably catastrophic. First posited by father and son team Walter and Luis Alvarez in 1980, the Alvarez hypothesis is a symbol of how brutal life on our planet can be. In 1979, with hammer and chisel, they had extracted and examined a sample of the Cretaceous-Paleogene border in the Italian Apennines, half of the fist-sized rock belonging to the age of the dinosaurs, and the other to a world of small mammals. Through the middle of it, a fine, dark, wavering line was the only remnant of a catastrophic event that had ended the dinosaurs' reign. In that delicate layer, Walter and Lewis discovered inflated concentrations of iridium, a metal that's extremely rare on Earth, but which, they theorized, was delivered by an asteroid. 66 million years ago, an 80-kilometer-wide asteroid smashed into the Yucatan Peninsula in Mexico, obliterating itself in the process and spreading iridium in a fine layer over the entire globe. It triggered a string of catastrophic climatic and tectonic changes that, in a mere 30,000 years, decimated life on Earth. Dinosaurs died, never to return, along with 75% of all species on the planet. The living world was utterly transformed. And yet, this brutal impact and its subsequent horrors were nowhere near the worst mass extinction event the Earth had seen. Nearly 200 million years deeper in time, at the end of the Permian period, Earth's biodiversity plummeted in a geological blink of the eye. This time, there was no external agent of destruction. The Earth itself conspired to call forth its Armageddon. Huge volcanic eruptions spewed lava, dust clouds, and gases, transforming the planet. The changes drove ancient species from many different families to extinction, including trilobites, ammonites, and some of the earliest land-dwelling mammals and reptiles. 96% of all marine species and 70% of terrestrial vertebrates were lost. Known colloquially as the Great Dying, this has been widely held as the most deadly of Earth's many extinction events. But there is one more candidate for this grisly crown. Billions of years deeper in time. The evidence may not be as clear as the boundary rock Walter Alvarez held in his hand, but much, much closer to the formation of our world, there is record of an event so catastrophic that it almost saw the loss of all life on Earth. In the Archean world, at least 2.5 billion years ago, the microbial ecosystem thrives in blissful ignorance of the coming apocalypse. Life is limited to diverse bacteria clusters around hydrothermal vents peppering the ocean floor, feeding off the various minerals disgorged from these smoking chimneys. But these are crowded microcosms. These microbes can only stray so far from the life-giving chemistry on which their metabolisms rely, and the hydrothermal chimneys can only supply so much. So, new metabolisms emerge. Through mutations of the genetic molecule, the bacteria learn to do new things with the chemicals they're surrounded with. Not only that, but they can exchange their newfound skills with their sisters, in a genetic handshake of which only these simple life forms are capable. Bumping against each other gently in the crowded vent metropolis, two microbes can briefly link their membranes and shuttle tiny packets of genetic material back and forth, constantly trading genes and creating new combinations within their own cells. This was the source of staggering diversity in these gloomy seas, and the mechanism that birthed an entirely new innovation, one that was to ultimately transform the face of the planet. That innovation was of pigments, tiny specks that would appear purple to our eyes, but which are capable of absorbing specific wavelengths of light and capturing the energy. Suddenly, microbial life forms have a brand new source of energy available to them: the light from the sun. Sunlight is inexhaustible and easily accessible, as long as you can survive the waves and tides that haunt the shallows. To the first light-loving microbes in a chemical world, their innovation opened the doors to a brand new kind of existence. These phototrophs could eat the sun. This was the birth of photosynthesis, but it wasn't the photosynthesis we learn about in school. It was a strange, noxious kind of chemistry with exotic ingredients. Purple-colored bacteria fed on the sun's infrared light, beyond the visible spectrum. They used hydrogen and dissolved sulfides to complete their reactions and produced solid yellow sulfur and corrosive sulfuric acid as byproducts. The early photosynthetic world was a toxic, stinking mire. But this wasn't the cause of the catastrophe to come. Even after bacteria learned to eat the sun, innovation continued. Through the microbial gene exchange and much trial and error, iterative improvements were made to the new metabolism. New, green pigments absorb red and blue light, capturing more energy than ever before. And a new, simpler kind of chemistry is developed, one that relies not on noxious sulfur, but on ubiquitous water. In this new and improved form of photosynthesis, the sun's energy is combined with carbon dioxide and water to power a cell's metabolism. This is the successful pathway that has been handed down through billions of years, and upon which green plants and algae rely to this day. But this wildly successful new pathway had a dark side. It created a waste product, more deadly and noxious than any sulfur that came before. A toxic waste product that would bring disaster even to the organisms that made it. And one we are still living with today: oxygen. Oxygen may not seem so terrible to us. Indeed, we can scarcely imagine a world without it. Every animal on Earth today relies on oxygen for its own metabolism. But in the late Archean and early Proterozoic, 2.5 billion years ago, it was a novelty to which the entire planet was unaccustomed. In September 1844, the southern shores of Lake Superior were a wilderness of hardy white pines, casting long shadows over a softly undulating landscape of ice-smoothed rock. A small team of prospectors are working their way through this landscape, led by one William Burt. He is a geologist and surveyor sent to the northern peninsula of Michigan to seek out new metal ores. Michigan already has a thriving copper industry, and investors seek to exploit ever more of the state's natural bounty. So, late one September afternoon, as the sun casts a golden glow over the landscape, William Burt squints and peers at his compass. Something isn't right. The sun in his eyes tells him he's facing west, but the compass needle points straight ahead. He turns to the north to look across the glittering waters of the lake, but the needle still points resolutely into the hillside. At Burt's instruction, the surveyors set up camp here and begin their investigations to discover the cause of the compass's strange behavior. Several days of digging, hacking, and blasting later, the prospectors stand before a clean, unweathered rock surface, the likes of which the small team has never seen. The rocks are vivid red and jet black, strikingly arranged in smoothly alternating layers, some mere millimeters thick, others half as tall as a man. Later testing will reveal that iron makes up more than 30% of these rocks, compared to just 5% on average in the Earth's crust. With little more than a compass needle, William Burt had struck Michigan's black, stony gold. These iron-rich rocks would come to be known as banded iron formations, and they would bring Michigan steaming into the Industrial Revolution. But banded iron formations have more to offer than just their mineral resources. These rocks, now exploited in northern Michigan, were birthed in the Proterozoic oceans 2.4 billion years ago. They are the lucrative product of a world in crisis. With the invention of water-based photosynthesis, oxygen was being produced and emitted into the oceans for the first time in Earth's history. Oxygen is a remarkably reactive element and will instantly combine with almost any other element, creating brand new compounds. In the Proterozoic oceans, the newly created oxygen reacts with the green iron hydroxide suspended through the water column, transforming it into iron oxide. Rust. Spreading out from the shores where the photosynthetic bacteria thrive, the waters turn an apocalyptic blood red. Over time, the iron oxide settles, floating down through miles of water to be deposited on the ocean floor. They become the crimson iron-rich layers in the banded iron formations. But a curious thing is happening in the shallows. While the first innovative microbes may have evolved to use the efficient new form of photosynthesis, they haven't yet evolved a resistance to oxygen. Without protection, the waste product builds up in their cells, reacting aggressively with the delicate chemical machinery that keeps them alive. The microbes have no protection because they've never needed it. Until now. So, these new bacteria are suffocated by their own waste gases, dying in droves just as they reach the peak of their success. When populations grow too large, the flow of oxygen in the ocean exceeds what can be removed by iron, and the entire shallows are oxygenated. The toxic oxygen sweeps like poison gas over the bacterial communities lying prostrate in the sun, killing them where they lie. With the sun-loving microbes slaughtered, oxygen production all but stops and normal service resumes in the ocean depths. Muddy shales and silica-rich cherts accumulate, free of iron oxide, covering the red sediments. But the oxygenic cleansing isn't absolute. Not all photosynthetic bacteria are wiped out. Life finds a way. These microbes find their way back to the dappled coastal waters. Their populations bounce back, and they begin to pour oxygen back into the ocean once again. And so, the cycle repeats. Millions of years of blooming and dying, of oxygen levels rising and falling, of red iron oxides alternating with black anoxic silicates. Gradually, pulse by pulse, the banded iron formations accumulate. They are an elegant, deep-sea record of a bitter battle for survival in the shallows. Banded iron formations like the ones discovered by William Burt in Michigan are found today on almost every continent. They formed across huge swathes of the deep Proterozoic ocean and record pulsing oxygen levels lasting 200 million years. But this is just the beginning of the oxygen catastrophe to come. Geologists examining the rocks of the earliest Proterozoic notice a striking transition around 2.4 billion years ago. The black basalt and its black sands and black muddy riverbeds for the first time turn red. The phenomenon is more widespread than just the deep-sea banded iron formations. This is a transformation that took over the entire globe. Around 2.4 billion years ago, the Earth rusted. But how did this happen? How did the photosynthetic microcosmos break out of its seemingly endless boom and bust cycle? With enough time, the photosynthesizers have chance to innovate, exchange, and evolve. Eventually, they evolved to withstand their own waste gases. Oxygen no longer poisoned them straight away. They could live long enough to grow their numbers, bolster their population, and maintain their tenuous grip on the sunlit shallows. Without periodic devastation, they could soak up the sun and belch out oxygen uninhibited. Before long, the seas ran out of iron to soak up the excess oxygen, bringing about the end of widespread banded iron formations. Oxygen begins to fill the oceans, dissolved in the water, beginning at the shore and spreading inexorably into the darkest depths. Ocean currents bring tongues of oxygenated water into the furthest reaches of the Proterozoic oceans. Oxygen's silent, deadly spread is catastrophic for the rest of the biosphere. Those crowded microbial communities clinging to hydrothermal chimneys in the dark never change their ways. They never exchange their genes with sun lovers, and they have no resistance to toxic oxygen. They are decimated. Even those that survive the initial cull are deprived of the chemicals on which they depend. Oxygen reacts with iron, sulfur, and manganese emitted from the vent, oxidizing it and locking it away in deposits, now inaccessible to these primitive microbes. As oxygen spreads through the ocean, so microbial city after city fall, gassed, poisoned, starved, and rusted to death. There was no escape. The photosynthesizers had brought about a new world order in which there was only room for those tolerant to their regime. But even this was not the end. The thin layer of iridium that Walter Alvarez and his father discovered in Italy in 1980 was a record of the asteroid that started the KT extinction. The impact obliterated everything for miles around, sent shockwaves around the globe, started forest fires, and filled the skies with smoke. But, for the majority of the biosphere, death came much slower. During a global winter that gripped the planet for years after, or during intense warming that followed. It was the climatic after-effects that dealt the final blow. So too, with the Great Proterozoic Extinction. In 1868, just over the Canadian border from the then thriving iron mines in northern Michigan, exploring geologists discover another curious rock formation on the shores of Lake Huron. Here they uncover a strange amalgam of pebbles and boulders set in a fine grey cement-like matrix. From tiny gritty grains to boulders weighing several tons, the stones are a colourful assortment of many different rock types. Speckled white and grey granites, striped orange jaspers and greenstone glinting in the sun. There are no matching source rocks for these exotic pieces for hundreds, even thousands of miles. The largest boulders are too heavy to be moved by wind or water. To the 19th century geologists, their presence here is a mystery. It is as if they have been dropped from the sky. Today, we know many more examples of these mysterious exotic rocks from later periods of Earth's history. They are called erratics, and they are indeed dropped, although not from the sky. Rather, from melting glaciers. Pebbles and boulders are plucked from the bedrock and transported along vast icy highways before being deposited unceremoniously when that ice melts away. Only the unstoppable progress of ice has the power to move so much rock so far from its source. The erratics around Lake Huron are exceptional in both their age and their variety. Dating to at least 2.1 billion years ago, they are the remnants of not just one glacier, but a vast ice field, transporting debris across thousands of miles. The so-called Huronian glaciation, named for these deposits, was an ice age like no other. It was the ice catastrophe that followed the oxygen catastrophe, and the nail in the coffin for much of life on Earth. The seas filled with oxygen and wiped out the deep-sea microbial communities. But the photosynthetic communities continued to thrive, pumping out more and more oxygen until the seas could hold no more. So the waste oxygen began to eke into the atmosphere. Here, it reacted with exposed rocks, but it also reacted with other gases in the air. Most notably, it tore apart molecules of methane, transforming them into carbon dioxide. And while we know carbon dioxide today to be a warming greenhouse gas, on the early Earth, methane was a much more potent insulator. As the skies were stripped of their downy methane blanket, global temperatures dropped. The greedy, surviving photosynthesizers continued to gobble at the carbon dioxide in the atmosphere, depleting the planet's insulation even more. The Earth was then plunged into an ice age of unimaginable proportions. The sun shone less brightly than today, and with the planet losing what little heat it once retained, the lakes, rivers, and oceans began to freeze. Ice shelves edged towards the equator, spreading like freezing corruption from the shallows over the deep oceans. Before long, the Earth was a snowball planet, head to toe in a cloak of featureless ice. And so it remained for 300 million years, with every continental shelf frozen solid, covered by ice 100 meters thick. Even the voracious photosynthesizers met their match. The shallow seafloor froze solid, entombing microbial communities in solid ice. Deeper water that escaped the freeze was black as night below the thick, opaque ice. For microbes that eat the sun, this endless night was an inescapable death sentence. After reaping devastation on the archaic life forms in the deep ocean, they are eventually the very agents of their own destruction. Together, the chemical revolution and the ensuing climate crisis combined to bring about the biggest mass extinction that the Earth has ever seen. It's often overlooked in the face of more recent extinctions where staggering numbers of species are lost, or huge, charismatic animals like the dinosaurs disappear forever. But the Great Oxygen Extinction saw primary productivity, the production of organic compounds by life, plummet. Scientists estimate that 99% of all life on Earth was lost between 2.4 and 2 billion years ago. The bountiful microbial oceans of the Archean were wiped out forever, and the majority of those ocean ecosystems would never recover. Just 1% of life clung on through the toxic ice age in deep ocean refuge untouched by the poison gas, or in rare, warm coastline oases that somehow escaped the global freeze. All life on Earth today is descended from those lucky few who made it, against the odds. Oxygenic photosynthesis, a chemical innovation made by tiny bacteria nearly 2.5 billion years ago, is the fundamental root of most of our modern ecosystems. And yet, its invention almost brought about the destruction of all life on Earth. You've been watching the entire history of the Earth. Like and subscribe and leave a comment to tell us what you think. And we'll see you next time.